All right, so last class, most recently, we talked about Box-Jenkins models, right? These non-seasonal ARIMA models, and we're going to kind of maybe do like a little bit of loose ends here. We'll conclude with an example. I wanna first talk a little bit about some of the underlying mathematics, and the underlying mathematics behind these ARIMA models is pretty deep, particularly for kind of the baseline of our program. And then that's part of the challenge of teaching and learning these models is this mathematical depth. So we'll discuss it in a little bit of detail. I'll give you kind of a big picture overview, and then we'll conclude by talking about a really important diagnostic test that you need to do after fitting your model, referred to as the Ljung-Box test. So let's start with this idea of stationarity, right? So in our most recent lecture, we talked about the fact that to be able to fit these models and how well our ARIMA models work depends upon whether or not the data is stationary, right? And what did stationary mean? Stationary had basically three components to it. The the data had to have a common mean, which means that our scatter plot looks like it's like a horizontal line. So that was kind of the first part of stationarity. The second part was we needed a common variance, right? If we look at the kind of fluctuation about this horizontal line, that fluctuation needs to be, roughly even. You don't want to have more or less fluctuation at certain points of time. And then finally, right, maybe one of the trickier parts was that we needed the correlation between any 2 points in time, right? The correlation in y between any two time points to depend only on the time difference, right? So for example, the correlation between all observations separated by 2 points of time is the same, right? And those were kind of like the three defining characteristics of stationarity. Now, of course, in real life, it's exceedingly rare to have like an actual data set that's stationary. However, we saw that you can take a data set and perform transformations on it, and these transformations could then result in a data set that is stationary. So often we're working with some transformed data set. Now, in addition to stationarity, which is at least surface level, a pretty straightforward concept and one that we can often assess with just kind of our eyeballs in a scatter plot, there is a second defining characteristic, and the second defining characteristic is called invertibility. And the actual mathematical definition is pretty technical. I'm not going to get into like a formal mathematical definition of it, but like big picture, intuitively, it's saying that the weights given to previous observations get increasingly smaller and smaller. And you might say, well, what are you talking about? The weights are getting smaller and smaller and smaller. And I'll give you a little bit of insight on that, I think, in the next slide. So math fact, you can hopefully take my word for it. Although I think I illustrate an example of it a little bit later. If we have an autoregressive model with some finite number of terms, right? Some finite number of terms p, we can rewrite that model as a moving average model that has an infinite number of terms. Similarly, if we have a moving average model with some finite number of terms, right? Some finite number q, we can mathematically re-express that as an autoregressive model with an infinite number of terms. All right, so sounds maybe a little bit crazy. It's not too hard to illustrate at least one of those. And again, I think we'll talk about it in a little bit. But you can get a sense of some of kind of the underlying math that I'm doing my best to shelter us from, and I'm not going to go too deep into it, but I do think we need to have at least a little bit of an awareness of it, and I'll talk about why that is in a bit. So this invertibility condition that I'm talking about can be thought of as the idea that when we have these infinite models, or these models with infinite terms, that the coefficient of these terms are converging to zero, right? That's our invertibility condition, is that when we write these things as the infinite models, that the coefficients of these infinite terms is converging to zero, getting increasingly close to zero. Now, in terms of actually seeing whether invertibility and stationarity is satisfied for a given equation, mathematically what this ends up boiling down to is looking at the roots of these equations. And you might say, like, well, what are we talking about? These aren't polynomial equations. Later in the class, we'll actually see that we can write these things as these kind of interesting polynomial equations. And basically, invertibility and stationarity boils down to looking at roots of the equations and seeing whether these roots have a magnitude less than 1. So, right, remember, it's maybe been a while, but when you look at the root of an equation, we can have complex numbers as roots. Remember that? And so, right, we have to look at the complex plane, and we have to look at where the root falls in the complex plane, and we want that root to be somewhere within the unit circle, which I know probably to a lot of us is kind of like what is he talking about? It's not going to be on a test, I promise you. I'm just giving us like a little bit of a big picture where this is coming from. So hopefully you can at least take my word that, right, all these things could be expressed as these polynomials. Probably we're all comfortable with the idea that polynomials have roots associated with them, right? And that, right, the whether or not invertibility and stationarity is satisfied, it turns out is equivalent to like looking at like whether the roots of these equations satisfy certain conditions. So whether these roots are real or complex or a mixture of the two, that's what actually ends up determining like the underlying shape of our autocorrelation and partial autocorrelation curves. It tells us whether it dies down in an exponential manner or a sinusoidal manner, or, right, some kind of mixture of the two. Now, a couple math facts for us. Again, unfortunately, I'm not going to prove a lot of this, so the alternative to that is just kind of taking what I'm saying on faith. Moving average models. Actually, I think we might prove this first one, or at least I'll make it a little bit more explicit. Moving average models, it turns out, are always stationary, but they may be that there exist moving average models that are not invertible. On the flip side, autoregressive models are always invertible, but not necessarily stationary, right? That is, it's possible, given a set of data and a specified model, for parameter estimates, for SAS to create parameter estimates for values that violate some of these conditions. And so, right, the reason I'm bringing this up is because this probably will happen to you. You might at some point try to fit some model and you're going to get an error from SAS. And why is SAS giving you an error? Most likely because for the model you specified, the optimal equation is violating one of these conditions, right? If you're fitting a moving average model, then the model you just fit is violating the invertibility condition. If you're fitting an autoregressive model, then the model you just fit is violating the stationarity condition. All right. So let's look a little deeper at a moving average model. It's actually not too hard to show, right? If you go to the equation from last week, it's just like it's like a little bit of 505, little 506, little 512, to show that the expected value is just delta, and that the variance is just sigma squared plus sigma squared times the sum of the theta I squared. Right? And notice what? Notice that the expected value and the variance do not depend upon t, right? That's the key observation for us to make. If you want to derive that expected value and variance, go ahead. It's a nice kind of refreshing exercise. Just, I guess it's really just 505 is what you're applying, and some of, right, those rules for distributing expectations and variances. So I encourage you maybe to go ahead and derive this on your own. I'm not going to put it on a test. And if you'd like me to have a meeting with you and kind of walk you through it, I'd be happy to do that. But the key idea is looking at these equations and observing they don't depend on t, right? So that's showing that our first two conditions of stationarity, that the mean and the variance don't depend upon t. Right? The third thing that we need to show for stationarity is that the correlation between observations only depends upon how many time points separate those observations. Right? That the correlation between y1 and y3 is the same as the correlation between y51 and y53. Right? And again, the correlation's not really too challenging to show. We could use some 505 tricks, right? You may or may not remember from 505, we had this formula that the correlation between two random variables is just the covariance of those random variables divided by the product of their standard deviations. Right? So that's a more general XY kind of method of presentation, similar to what you might have seen in 505. Right? In time series, our x and our y are something like y sub t and y sub t plus k, right? Two time points separated by, or two observations separated by k time points. And, right, we just showed that the variance of the y's doesn't depend on time. So y sub t and y sub t plus k have the same standard deviation. So that formula, right, a formula boils down to the covariance of y sub t plus k, right, sigma y times sigma y, which is just sigma squared y, or the variance of y, which we had on the previous slide, remember? So we know that variance formula. So we just need to kind of figure out the covariance. Right, and that correlation, remember, I think 512 we use this notation, that's the Greek symbol rho, right? So rho sub k, we could call this the theoretical autocorrelation value. Right, we had the SAC, we talked about, that's the sample autocorrelation, right? The autocorrelation in our sample, which is supposed to be, right, our best guess for the TAC, the theoretical autocorrelation, or the true autocorrelation. All right, so we could show, and again, if you want, I would encourage you to try it on your own. If you're having troubles, you could talk to me about it. If you just want to say fuck it, I don't want to worry about it, that's fine too. It all depends on how invested you are or aren't in some of this kind of mathematical foundations. But we could show, so for a first order moving average model, that the covariance between y sub t and y sub t plus 1 turns out to be negative theta 1 times sigma squared. If I plug that back into my formula from the previous slide, then I end up getting that rho sub 1 is negative theta 1 over 1 plus theta 1 squared, right? So we can come up with these precise formulas for our correlation. Now, still assuming a moving average model of order 1, again, it's not that hard to see. I'm not going to spend our class time proving it. I would encourage you to take a look at it and try it on your own. Unofficial homework assignment, that the correlation between y sub t and y sub t minus k for any k more than 1 is going to be 0. And that, of course, implies that the correlation is 0. Right? Which tells us what? It tells us what we already knew from last class, or at least what we learned from last class, what I stated last class, is that a moving average model of order 1, the SAC and the TAC, the TAC, the autocorrelation function cuts off at order 1. That is, it goes from having a numerical value and then abruptly becomes 0 and then stays 0, right? For any value of k that goes on. Yeah, again, I'll leave it to you to prove it. Again, it's not going to be a test question. I'd encourage you to give it a shot, and then if it is the kind of thing that you're interested in or curious about, sign up for office hours, come visit me in office hours. I'd be more than happy to kind of walk through it with you. Now, more generally, we can show the following. It's really just the same calculations, and if we have a more general moving average model of order Q, we could show that theoretical autocorrelation is, right, that summation on the top divided by that summation on the bottom. So we have an explicit formula for all values of k all the way up to q. And then as soon as we get to q, anything after it is 0. Right? So we're again showing a little bit more explicitly what we stated last class, that if you have an autocorrelation function that looks like it goes up to some point q and then boom, just drops off, plummets, cuts off is the phrase we used, and becomes 0 after that, that's indicative of a moving average model. Now, what about invertibility? So what have I shown? I've shown that, and again, you might be taking some or even a lot of this on faith, but at this point, I have shown what I stated earlier, that a moving average model is in fact always stationary. I'm going to give you an example that kind of shows a little bit about its lack of invertibility. And so what I encourage you to do, again, I'm gonna leave this to you. Here are two different equations, right, for some value theta. So like one of them is theta, one of them is 1 over theta. So one of them is 2, for example, and one of them is 1/2. So two different equations, but it turns out that these two different equations will lead to the same autocorrelation function, right? Which is a little bit kind of crazy mathematically. And it implies what? It implies that to get uniquely specified equations, we need to apply certain restrictions on our equation. Yeah, so the implication, certain conditions are necessary to assure that a given autocorrelation function will induce a unique model. And so we're going to talk about what those conditions are in a few slides. Not immediately, but before this lecture is over, we'll talk about what these conditions are, right? And essentially, these are the conditions that are going to help guarantee invertibility. And when these conditions are violated, that's when SAS is going to give us errors. All right, that's the moving average model, okay? And we saw the moving average model is the one that's sort of the most easy or the most tractable to work with, right? All of those calculations, right? You may or may not have done them, and I'm certainly not going to ask you to do it on a test, but it would be like a reasonable thing to ask you to do on like a 505 final exam, for example. 505 might have been a while ago, right? So you may or may not have the same capabilities now that you did then. But there was a time in your life that you could have derived those without too much trouble. Now, right, consider this model, right? Here's our autoregressive model of just order 1. Now, we did something, we've done things like this before. I think maybe most recently we did things like this with our exponential smoothing equations, where I can actually, like, I can recursively unravel this formula, right? I have a formula for y sub t. Y sub t equals delta plus, there's that circle slash. By the way, I figured it out. Circle slash is called phi. So we have phi times y sub t minus 1 plus a sub t. Now, recursively, I could now apply this formula to y sub t minus 1, right? And embed that in my formula. And then now I have an a sub t minus 1 in my formula, and a y sub t minus 2. And then I could recursively apply the formula to y sub t minus 2. And then now I'll have a y sub t minus 3. I can recursively apply it to that. That is, I could keep recursively peeling this formula back. And as I keep going back and back and back and back and back, I'm creating this sort of infinite formula. That is, right, hopefully we could see the claim I made earlier that an autoregressive model could be rewritten as an infinite moving average model, right? That's what I see there in the second equation. Y sub t is delta plus, right, this plus a sub t plus, right, this descending sequence of well, I shouldn't say that descending, this sum of phi sub I to the a to the t minus I. Right? That is, we can rewrite our moving average model we can rewrite our autoregressive model, sorry, as a moving average model with infinite terms. And so what we basically need to show, and part of the conditions that we need, is we need those phis to be converging to 0. Right? So for the variance to exist, which is needed for stationarity, the absolute value of the phi term needs to be less than 1, right? That should be apparent to us. And right, putting that condition helps us with kind of the problem, the non-uniqueness problem we saw before. So if we do that, then we can use like infinite sums to show that the variance of y sub t converges to sigma squared over 1 minus phi. Right, where we have this restriction that phi is less than 1, so so that thing's not going to be negative. All right, it's not too hard to show, right? For those of you that want to look at it, there's a kind of seminal time series book by Chatfield on page 42. They have the derivation. I'm happy to share it with you if you're interested. That that the autocorrelation function rho sub k is phi to the k. So what are we seeing here, right? We're seeing again what we stated last class, that for a autoregressive model, the autocorrelation, rather than cutting off, the autocorrelation dies down, right? That phi to the power k gets increasingly small, gets as close as you would like to 0, but never actually reaches 0. Right? More generally, we still figure out variances and covariances, right? When we're working with the autoregressive model, the typical trick is to turn it into an infinite term moving average model, because the moving average models are mathematically more tractable. Now, figuring out the coefficients is challenging and involves something called Ewell-Walker equations, which are very much beyond the scope of this class, at least, given the the fact that I'm not requiring a high level of mathematical prerequisites. All right. So big picture, right? Big picture. I know there's a lot that I've thrown at you. And you might be like, well, what am I responsible for? What am I not responsible for? Let's start with this, right? That a time series model needs to satisfy two conditions. A time series model needs to be stationary, and it needs to be, or I guess I should say the data needs to be stationary, and the model has to satisfy these invertibility conditions. Now, I can show you, I'm gonna show you what these conditions are for some relatively simple models. The conditions get crazier as we move to like more complicated models, but the reality is that most real life models can be fit in a pretty simple way. So like most time series models are going to be just like a first or second order moving average model or a first or second order autoregressive model, right? Most of our models will fall into this, at least when we're not considering seasonality. We'll talk more about seasonality next week. So what are my conditions that I need to guarantee invertibility? So first off, remember, a moving average model is always stationary. So we don't have to worry about that, but it's not always invertible. However, we can guarantee that our model is invertible as long as that coefficient theta, its absolute value is less than 1. For a second order moving average, we now have two coefficients, a theta 1 and theta 2. The invertibility conditions become a little bit more complicated. We need that the sum of the coefficients is less than 1, their difference is less than 1, and the absolute value of theta 2 is less than 1. Now for autoregressive equations, remember, autoregressive is always invertible but not always stationary. It turns out for stationarity, we need that the phi, right, that's what circle slash is, we need that the phi to its absolute value to be less than 1. And look at that, right? You got to love the symmetry of it. And for a second order model, we need that the sum be less than 1, the difference less than 1, and the absolute value of that phi sub 2 being less than 1. Okay. If SAS fits a model that violates these conditions, then SAS is going to give you an error. All right, that's it for the mathematics. Let's wind down with the important diagnostic tool, and then we'll look at where to access this tool in terms of an example. So we're going to talk about something. They're equivalent. You get the box-Pierce statistics. I'm not sure how to pronounce that person's name. I don't want to butcher it and insult them, so I just call it the Ljung-Box statistic. Right, Q for the first one, Q star. They're both essentially similar, both intended to do the same thing. The Ljung-Box statistic tends to work better, so I'm going to focus on that one. Right, the Q star, the Ljung-Box statistic. So what is this thing? The Ljung-Box statistic, or the Ljung-Box diagnostic, looks at the correlation of the model residuals. So we're looking at the A sub t's from our time series model. Now, if the model is properly modeling the dependency between the observations, then the residuals of our time series model should be independent, right? So kind of the big picture idea is, right, I have dependency in my data. I want that dependency to be soaked up by the model, to be absorbed in its entirety by the model, and have no dependency left over. That idea of leftover dependency is in my model residuals, my A sub t's. And so I could test whether or not my time series model has adequately addressed the dependency by looking at whether or not there's dependency in my A sub t's. Now, the Ljung-Box statistics tends to look at residuals. Like it's like an aggregate function of residuals up to some value k. Typically, we look at like increments of 6. So like 6, 12, 18, 24. Right? Very, very broadly, this is the way I believe it's presented in our textbook. Right? The null hypothesis is our model's adequate. The alternative is the model's inadequate. Our textbook talks about comparing the Q star to a critical value, but doing it in SAS, it'll give us a p-value, right? Which is something that we're probably more comfortable or more used to using. Now, something to keep in mind, Q and Q star are very general statistics that could be used to measure how well any particular model is removing dependency for the data, right? So for example, we could use them on an exponential smoothing model to see whether there's any dependency in our exponential smoothing model. We could also use it on just like a 512 model, right? So it becomes a little bit like a generalized Durbin-Watson test. All right, so let's tie all this together. Let's go to our paper towel example. I think we looked at this example in our exponential smoothing lecture. It has 10 years worth of monthly paper towel sales. So we want to analyze those sales. What's the first step? Exactly. First step, plot the data, right? Look at a scatter plot. So there's our scatter plot, right? We got our paper towel sales. There's the great paper towel crash of 1995, right? Your parents may or may not be able to tell you about it, and you know, they did have to live through it, unfortunately. So I look at this, and if I want to fit an ARIMA model, what's my next step? Well, yeah. If I want to do an ARIMA model, what's my next step? Well, first off, I want it to look stationary, right? And it does not look stationary to me. There is not a common mean, right? That does not look like a horizontal line. So I can start off by looking at the difference of the data. All right, instead of the y sub t, I look at the z sub t, where z sub t is y sub t minus y sub t minus 1. The z sub t looks like this. That looks pretty good, right? It says simple difference. I just click that little triangle button, right, in the upper left. That triangle button means difference. Certainly looks like a horizontal line, right? The variance looks roughly even. Now remember, we're looking for like dramatic departures from a common variance, and right, it looks like there might be like a couple cases where it like zigs down a bit or zigs up, but for the most part, it looks relatively even. It's not glaringly. There's not like a glaring obvious violation of common variance. right? Anytime you find yourself kind of waffling back and forth, you're probably okay. So now I have my data set, right? Or I have my stationary scatter plot. What's the next step? The next step, you're absolutely right, is to look at the autocorrelation functions. Yeah, data appears stationary after a single differencing operator. Next step is to look at the autocorrelation function. Okay. So here's our autocorrelation functions. We have the SAC and the SPAC. It's tricky. They both, to be honest, they both look like they cut off, don't they? They both look like they cut off. The autocorrelation looks like it cuts off after 1. The partial autocorrelation looks like it cuts off after 2. But we know that's not possible. So we have to think about which one we think cuts down the most. I think the autocorrelation cuts down the most. So if we were to buy into that, that means we'd be fitting a moving average model of order 1. That said, if you disagreed with me and said, I don't know, I think the partial autocorrelation cuts off the most, or if you just wanted to say, I can't even tell, there's nothing wrong with also fitting. Well, if we decided it was the partial autocorrelation cutting off at 2, that would be what? That would be an autoregressive model of order 2. There's nothing wrong with fitting both of those models and comparing them, right? And maybe that's something that you could do on your own. But for the sake of this lecture, I'm going to stick with what I'm seeing, which is a farther drop off between 1 and 2. Like I'm looking at that sort of 1 to 2, and then onward it's like a dying down in the SPAC. And in the SAC, I'm seeing like there's like a pretty high bar at 1, and then boom, it just looks all close to 0 from then on out as a moving average model of order 1. Yeah, SAC seems to cut off more abruptly than the SPAC. I'll admit it's a tough one to see. I've been doing this a lot longer than you have. There's nothing wrong with fitting multiple models and comparing them. If we buy into the SAC cutting off at lag 1, that tells us a moving average model of order 1. All right, so there it is. My graph, right, says IMA, right, integrated moving average. That 1, 1 is basically saying that we integrated it once. Integration is just, right, how many differences you took. So it's saying I took 1 difference, just the first difference, and it's a moving average of order 1. And look at that. These models are pretty powerful, aren't they? Like, this data looks so crazy. Like, if you were to look at that data in 512, you'd be like, how the heck am I going to fit that? But these ARIMA models do a very good job of chasing the data, don't they? Those predictions actually look pretty good. Now here, so how do I get this thing right here? To get this thing right here, I have to click the if you look over on the right hand side, we got our buttons there on our time series dashboard. If you click where it says P equals 0.05, you'll get something that looks like this. And this gives us the Ljung-Box test. The Ljung-Box test is what SAS is calling the white noise test. And if you were to mouse over, you can't do that because this is a PowerPoint. But if you actually had this dashboard on your computer and you moused over any of those bars, it would tell you exactly what the p-value of that bar is. Now, SAS has red lines, right? It has a red line we could see at 0.01. It has a red line at 0.05. So I could see that all these bars, right? In this case, the small bars are indicative of a large p-value. So all of these bars are well above 0.05. which is good, right? Because that means we failed to reject the null hypothesis, and our null hypothesis was our model was adequate. So this is basically indicating that our residuals are independent of one another. So this is a very, very, very good looking Ljung-Box test, or very good looking situation. Our dependency has been adequately modeled, has been sort of transferred into the time series equation successfully. Right, and then of course I can click on the beta hats to go ahead and get my model equation, right? So there's my model equation, right? I only have one coefficient, just order 1, so my coefficient's at negative 0.35. And then if I wanted some model fit diagnostics, I can click that sigma square button on my dashboard. And then that would give me something like this, right? Which I could then use these metrics to compare other models with one another, right? Would be maybe the primary use of some of these statistics of fit. I could compare mean squared error, root mean squared error. I could also, compare the IC and the BIC, that information criteria or Bayesian information criteria. All right, that wraps up our lecture.